thank you very much for inviting me here today. I'm going to start with linear systems in the beginning, and I'll be talking about the material by Anthrakis and Anthony Michael for the linear systems, and then I'll move on to nonlinear systems swiftly, and the material covered will be from Khalid's work, Vizori's work, and then Kovatovic's work. We'll be talking about control Lyapunov functions and optimal stabilization work. The course outline, it has been modified. We will cover these topics in 3 days, and we'll finish by Saturday evening, inshallah. Today I'm going to start with this part right now, and then we move to this part hopefully by the end of the day. How control developed? I know most of you have the idea and have the background. Early use was dictated by the gun control or radar control or stuff like that when it was First World War or earlier. And the techniques then actually evolved based on the block diagrams and transfer functions. And design tools were graphical, like the Laplace transform. So you were able to see the poles and calculate overshoots, which we still do, but then it was graphical method, and you had the body plots in which you had the magnitude and the phases, and you were talking about sensitivities and other aspects of the system. And it was supported by analog computing then. The field emerged, and drivers were space. This is time when World War II was over, and race between US and USSR, then USSR, now the Russian Federation, they had a race for space wars, Star Wars, stuff like that. And in those times, R.E. Kellman and others contributed. Kellman filters and other things, and moon landing was made possible. And so there was a rapid growth of subspecialties as well. In these times, actually, optimal control or other subspecialties of control systems emerged. And nonlinear systems theory also evolved back then. But in fact, it took a long stride after 1990s when Isidori and others were able to contribute the seminal work, which actually laid the foundation for today's developments. Computation tools were developed over the years by the advent of the microprocessors in late 70s and 80s, and there was impressive development of theory, especially linear theory, which is owed to Francis and von Ham. They actually introduced the idea of servo mechanism in linear systems, and that was one important development which actually led to other developments which are present-day development. And today's drivers are embedded systems. Everybody talks about Raspberry Pi and other stuff. We want to design controllers and implement on embedded hardware to do the specific job we want to get done. Now, many of us, unfortunately, just go and integrate things, make that edge bridge work and our ground vehicle work. We have no idea what is happening inside. So today's this session or this workshop is aimed to actually motivate you. I'm not saying that I'll be able to show you or teach you everything, but I will try to motivate you to go to the dynamics there and understand it, and then design a nonlinear or linear controller, and then apply on that Raspberry Pi, which is an embedded system, and then networks. Of course, we are doing surgeries while a physician or surgeon is sitting in England, and we are doing a surgery, which is a heart transplant, which is in Paris. So things are happening. And they're happening because that guy who is just doing a haptic sensor, feeling the same thing which a patient is presenting or something. For example, the movement of a needle over there is felt by the surgeon right here by a haptic sensor. Now, there's a channel, there's a whole network. The network has to be good. If network is not good, then controller has to be good because there's a life at stake. So networks, physics, of course. From mega to nano, we have gone to nanotechnology. Now we are trying to do things with our DNA strings. We are manipulating strings, or we are cloning things. to that level. Autonomy distribution, of course, things are distributed over the places. Industries have become vast and wide in areas, and they have different channels, different plants scattered around the whole industrial setup. And we would like that we have information about those plants which are working independently or dependently with something. Or we want to give them autonomy. They should make their decisions by themselves. Right? So plants working in an autonomous fashion. And of course, these are all exploding applications which have, and then hardware and software. Tremendous work has been done in hardware and software industry to support this. And this is my slogan, and I try to convey this wherever I can. Control everywhere, and I believe in this thing. That today you can find application of control virtually everywhere, starting from your socio-economic problems to traffic problems to engineering problems of course. Right? The intelligent traffic system or the Google which has now introduced, I don't know, they have been in some crashes lately, but they have developed an unmanned driverless vehicle. Okay? So we are sitting in the back seat of that car, doing some work or chatting, whatsoever, and the car is driving us to destiny. Power generation and distribution, just to give you some idea that these are all applications, we are all aware of it, because we are having some control background. Process control, of course, refineries and so many other stuff. Discrete manufacturing, robotics is one of the biggest clients of control people. And robotic industry is one of the biggest, and vehicles of all kinds. Then consumer electronics and intelligent software algorithms, or which are control algorithms, are implemented on these hardware to give you biomedical. Of course, this is the idea that surgery is happening from the remote, and then prosthetic hands, or actually taking nerve signals, EMG signals from brain to sensors, manipulating them in a way so that a person who is disabled, doesn't have an arm or doesn't have a leg, you give him the prosthetic arm or prosthetic leg, and the EMG signals actually now can move that prosthetic hand or artificial hand exactly the way we are moving. And it's thanks to all this development. This is one example, holding the cup and the egg. DNA strings I just mentioned, working with DNA strings to the level that you can actually give some signals, and now look at the level. This is nanometer level. And now I'm going to show you a level of telescope, which is designed to track the satellite. It's huge, it's mega structure. This is a nano structure. So you're controlling a tip of something at a nanoscale, as well as you're controlling things at a mega scale. So control has their application into a variety of things. Automotive applications are tremendous these days, especially with the advent of these smart cars or the computer-assisted cars which we have. Even the cars which are manufactured in our country locally, they have some onboard computer, right? Which do the diagnostics, or which give you some, which give the fuel injection mechanism, right? EFI controller, stuff like that. So starting from all these things which are written here, one of the interest is this heating, ventilation, air conditioning, and just have a look. Recently, not very recently, of course, it was in a decade maybe, climate control. This is one interesting application. There are two passengers sitting in one car. One is feeling cold, one is feeling warm. One wants air conditioning on, the other one. This is a household problem, right? So you're moving with your family, and your wife is feeling cold and you're feeling warm that day. Now you have to switch on the air conditioner, or you have to switch off, depending on how much you care for your wife. But science has solved the problem. It has given us this automatic climate control. For my side, it's cold, the other side is warm, or vice versa. And that's also a control phenomenon. aerospace, and that leads to the name UAVs. And you look at the advent. Of course, it's a military-specific advent at this moment, but we are reaching to these kind of things. In 2015, this is an old picture, and I think 2020 is something else. So things are moving by themselves. They're not moving by themselves. They're moving by efficient control design, right? And this is one of the good pictures I always try to show, because this is our future. We want to do this. Not for actually throwing missiles, but maybe doing something really nice as a civic application. Cooperative control. And recently, a few months back, they showed that they had, in IEEE Control System magazine, there are like 4 or 5 quadcopters, and they are building an abstract version of a wall cooperatively. Now, each quadcopter is responsible to place one brick, which is lying here, a small brick of course, it's an experimental setup, to a certain place. And now, if that quadcopter, that vehicle or UAV, gets late for whatever reason, things would have changed because the other guy has placed somewhere else. So it is like in real time simultaneous working. So that particular, each UAV has to find out where that has to go, depending on the program of course, and it has to make that wall. And they have done it iteratively. I will give you a reference if you are interested to that control system. I think it was August last year or September last year. Yeah. And this is network in embedded control systems, a topic which is emerging, and there is now a dedicated journal, IEEE Cross-Sections, on control of systems. Control of systems on network, right? For SON. So that is CONES, CONES. So that is one emerging field, actually, which is now taking over the world. And why I'm showing this? Because in this scenario, actually, in this application, there is a lot of room for all your students to get in. And recent results still talk about linear systems and treat the systems in a linear fashion. But with the time, they are now including the non-linear versions of it, because they are a little bit difficult to talk about, because you have to model the network, you have to model the system, you have to model the whole thing, and you can now have an opportunity to go and indulge into this kind of work and submit or contribute this field by using your novel ideas in the nonlinear theory. So let's get started with the A1. This is a problem we are very much familiar. I'm just looking at an open loop problem at this moment. I have a black box system, and I call that system as a control system, and this system is driven by an input, and I get an output. Or I want a desired response, and I get an actual response. So this is a typical input command that I give, and I get a response like this, or it could be like this, depending on what kind of overshoots I have. Okay, that will be the requirement of my desired or actual response. If I want the system to reach the input as quickly as possible, I would like that this may go overshoot, and that's fine. Typical example is gun. When I'm on a board ship, or in an aircraft, the gun is supposed to go and fire in a certain direction. At that point, when I'm giving the gun a signal to go to certain bearing, or computed by the radar, or so it's an autonomous thing or whatever, the first thing I would like before firing is that the gun moves there as quickly as possible. In that case, I'm not looking at this kind of response. I just want the gun to be there. The gun has to be there. Then, the gun can move around. So it can But I must ensure that one gun is overshooting, it should come back and in a reasonable time so that I can allow it to fire or the fire control solution. Meanwhile, the computer or the controller computes the fire control. Incoming target is coming and this angle is changing, and just have the dynamics in mind. It's very fast coming aircraft maybe, and you have a ship and you have a gun. That gun is not like T3. It weighs. It is a ton, more than maybe a ton in its weight. That particular thing has to move. Actuation has to be done. There has to be a servo. So that actuation has to be done in such a way that it remains stable. It goes faster enough. And all those things have to be incorporated using the information about those systems individually. So we'll have to deal with actuators, the high gain amplifiers, the system itself, the inertia, the motors, all those things. They all contribute and join together to become a control system. Okay? And from there, we actually go and do. Open loop versus closed loop is here. This is just one input and I get an output. Despite whatever disturbances I have, what the controller is required here to do, it may know about disturbance a little bit or more, and disturbance too. Now this was input disturbance and this is output disturbance. So controller may be designed once because it doesn't have information about the feedback. It doesn't have information how output is behaving like. So this signal doesn't go back, but in this case the signal goes back. So the controller has more information now, and now it is an error-driven system. Because now I'm looking at the difference between input and the output, and as the difference between input and output reduces to zero, I don't have any signal. So ideally, the input becomes zero when I reach there, which is the case. Unless I have disturbances. When I have disturbances, the output will not be exactly that, but there will be some signal coming in. That means there will be an error. So despite the reason we had output minus input 0 in the beginning, but since there was disturbance, that disturbance actually now initiated in a feedback way, but that was not possible here. So that's why this system is better than that system, of course, because it can take care of disturbances and it can still give you the output response as expected. But it has disadvantage as well. This channel here, if this is not a good gain, usually we look at unity feedback system because both theories based on unity feedback system. But if this is not a good gain, it can actually do the worst thing. Maybe we have small trigger and the gain is high. This can actually jeopardize the whole thing. So there is a price of a bad design as well. It's not going to be good all the time. So we have to go back and simulate the systems. I'm going to show you here the block. We have to recheck, redesign. There's a step-wise procedure, and I've borrowed this one from Nonlinear 6th edition. There's a systematic procedure. You have equation, you have a model, you start with the control design, you get back, you reach, and you get the desired performances, analyze, design, and test, and you go back. If you have any issues, you have to go back. Back here, tracking problem. Let me ask you a question. What kind of signal a geostationary satellite poses to this antenna? This antenna is required to track all these things. So let's look at the first part. What kind of signal is this getting to track in this case? Geostationary. That means I am standing on the earth and that is also moving the same velocity. Because I am moving when I am standing here. We all are moving, no matter we like it or not. We all are moving with a certain velocity. It's huge velocity. Earth is rotating around. So what's this signal? Step? Did somebody say? Something like that. स्टेप किसने स्टेप कहा था? सुबह से स्टेप, हाँ स्टेप क्यों है? क्योंकि हमेशा हमें जाके प्लॉट करना चाहिए। आपने बिल्कुल सही कहा। तो देखें फिर स्टेप इसलिए है कि मैं भी खड़ा हूँ और वो भी खड़ा है और वो भी मेरे हिसाब से मूव कर रहा है। एक्चुअली मैं उसको देख रहा हूँ तो मैं एक कांस्टेंट सिग्नल देख रहा हूँ, कांस्टेंट सिग्नल और व्हाटएवर एम्पलीट्यूड step signal. How about the other one, that line orbiting at a different velocity than Earth? Ramp. It is a ramp, and the side which is accelerating, going somewhere else or coming towards right? So these are the signals, and our tracking system should be able to handle those signals in a meaningful way in order to get this response as desired, right? And this is that one example. I have this tracking system, and now why I am showing this picture? Because I want to come to this part. Every individual component here has a model. Every individual component has a model, and that constitutes one of the block diagrams. And every individual block may have a nonlinear phenomena coming in. Okay? So, it's not that only plant will be nonlinear. It may be that actuation is nonlinear. It may be that the sensor is nonlinear. Now, either we have two main ways. And then one is that we look at the whole thing in a holistic way. That would be really difficult, right? Nonlinear, and we have to establish conditions that what if signal goes here and gets here, what would have been happening with that? And will that signal be worthy to be injected to the next level? Will that signal be worthy to inject to the next level? And so on. Because it's not necessary the signal we injected did what it was supposed to be doing in that block or was manipulated in that way. So we have to look. So we have to start with looking at each individual block in a different way now. Okay. There are three techniques of looking at physical systems and bringing it to maths. One is myth and one is maths. We talk about maths first. This pattern is only MATH and YTH. Okay, maths. One is transfer functions. We all know about. The other one is I want to solve transfer function. Whenever we say transfer function, that means we have to bring or we have to take that model, get into some other domain. And now, since that domain is like a wonderland, so Alice has to go and she has to get back. अगर वो ट्रांसफॉर्म डोमेन में गए तो उन्हें वापस भी आना, वरना फिर फायदा नहीं। उसकी ये लिमिटेशन है क्योंकि ट्रांसफॉर्म की जो बात की, इसका मतलब कि लिनियरिटी आ गई। ऐसी चीज़ जो मुझे पता हो कि जब मैं जाऊँगा तो वापस भी आऊँगा, अदरवाइज फिर वो ट्रांसफॉर्म नहीं रहा। तो ये लिमिटेशन है। इस लिमिटेशन की चक्कर नहीं होता है कि हम एक नॉन लिनियर सिस्टम को ट्रांसफॉर्म डोमेन में लेके नहीं जा सकते। अगर लेके जाना तो उसको लिनियर करना होगा, फिर लेके जाएंगे, वापस आएंगे, सॉल्व करेंगे, तो पर्पस लॉस। तो क्या हम ट्रांसफॉर्म्स की बात करेंगे, लेकिन मैं उसको ट्रांसफॉर्म नहीं कहूँगा आगे चल के। इट विल बी डिफ्यूमॉर्फिक मैप, इट विल बी समथिंग एल्स, विल नॉट रियली से दैट इट्स अ ट्रांसफॉर्म। ट्रांसफॉर्म इज अ लिनियर प्रॉपर्टी। दूसरी चीज़ ट्रांसफॉर्म की बात ये है कि चाहे टाइम कोई सा भी हो, मैं जब भी ट्रांसफॉर्म में जाऊँगा वापस आ सकता हूँ। तो इसका मतलब कि इनिशियल कंडीशंस को मैं उस तरह कैप्चर नहीं कर सकता, जो कि कभी कभी बहुत इंपॉर्टेंट हो जाती है, मोस्ट केसेस दैट्स। तो मेरे पास एक रास्ता तो वो था कि फ्रीक्वेंसी डोमेन में जाऊँ, एस डोमेन, जी डोमेन, डिपेंडिंग ऑन मेरे पास डिस्क्रीट इक्वेशंस हैं, इंडिपेंडेंस इक्वेशंस हैं, मैं उनको सॉर्ट आउट करूँ एंड देन आई कम बैक। दूसरा तरीका ये है कि डायरेक्टली टाइम में ही बात करूँ। अब टाइम का मसला ये है कि आई नीड सॉल्यूशंस टू इक्वेशंस। क्योंकि अगर मुझे ये नहीं पता कि उस इक्वेशन का सोल्यूशन क्या है, तो व्हाट टू टॉक अबाउट इट। ये इक्वेशंस कहाँ से आती हैं? इक्वेशंस आती है स्टेट वेरिएबल। आपको आइडिया है? आई एम श्योर स्टेट ट्रांसफर फंक्शन का लिमिट इसलिए जरूरी है कि ट्रांसफर फंक्शन क्या मतलब है? ट्रांसफर फंक्शन आउटपुट और इनपुट। اوکے آؤٹ پٹ آپ جب لیتے ہیں فار ایگزامپل اتنا سسٹم ہے آگے چل کے بہت بھی پائے گا Can I just go and write like کیا لکھیں compare this one with this thing کہ میں لکھتا ہوں کہ ٹھیک ہے C of S is some value and یہ ایک الجبرا کی ایکویشن ہے اس کا اگر میں لکھوں یہ آیا کہاں سے تھا یہ آیا تھا کہ میں اس کو کہتا ہوں یہ کوئی ویریبل ہے اور یہ میرا ان پٹ ہے یہ آیا اس طرح تھا کہ یہ بنا میرا سی ڈبل ڈاٹ پلس 2C ڈاٹ پلس C ایکول ٹو R ڈاٹ پلس R یہ میرا سسٹم تھا جو کہ ایکٹیو سسٹم تھا میں کہوں کہ D اسکوئر C of T اوور dt اسکوئر پلس 2 DCT اوور dt plus CT equal to dr over dt plus r ایسے تھا اس کا میں نے یہ کیا سادہ کیا اس کو میں نے اس طرح لکھا اور اس کو میں نے کہہ دیا کہ یہ ٹرانسفر فنکشن میں نے سادگی کے ساتھ جب اس کو میں لے کے کیا تھا ادھر اس سے اس میں یہ آئیڈیا ہے میرے خیال میں نا میں پاس میں کر رہا ہوں اور جب میں اس میں لے کے کہتا اس کو تو جب میں ادھر جا رہا تھا تو میرے پاس دو آپشن تھے یا تو میں ادھر اس کے ساتھ انیشیل کنڈیشنز کو بھی ڈالتا لیکن میں نے کہہ دیا کہ نہیں جی لینئر ٹائم انویرینٹ ہے جب ٹائم انویرینٹ کی بات کرتے میں لینئر کوئی فرق نہیں پڑتا کبھی بھی شروع کروں کام وہی کرنا ہے ٹھیک ہے ادھر سے ادھر گیا ادھر سے ادھر گیا اور میں اس کو اس طرح کر کے گرافیکل ٹول استعمال کیے میں نے اپلائی کر دیا سالو کیا انپٹ اپلائی کی اسٹیپ اور ریمپ اور جو بھی ہو ڈپینڈنگ آن کے سسٹم کس کو ہینڈل کر سکتا ہے کیونکہ یہ سسٹم ساری انپٹس کو ہینڈل نہیں کر سکتا ٹائپ ہوتی ہیں سسٹم کے ٹائپ 0 ٹائپ 1 ٹائپ 2 ڈپینڈنگ آن دیٹ آئی واز ایبل ٹو سالو اٹ تو یہ ٹرانسفر فنکشن تھا ہاؤ اباؤٹ دس میرے پاس ایکویشن ہے اسی طرح کی ایکویشن ہے لیکن اب اس کے ساتھ میں اس کو فلیکسیبل اس طرح بنا رہا ہوں کہ میں ٹائم بھی کیپچر کر رہا ہوں میں دوسری چیزیں کہنا رائٹ اوے رائٹ سم تھنگ لائک دس اس کا میں ایک کام اور کر سکتا ہوں میں آگے کروں گا آپ کے ساتھ آئی کین رائٹ این آئی او ماڈل انپٹ آؤٹ پٹ ماڈل میں بنا دوں گا اس کا لیکن اس کو میں ٹرانسفر فنکشن نہیں کہوں گا اس انپٹ آؤٹ پٹ ماڈل بناتے ہوئے میں ایک کام یہ کروں گا کہ آئی ول لک ایٹ دی کریکٹرائزیشن آف سگنلس انپٹ سگنل کس قسم کے ہو سکتے ہیں آؤٹ پٹ سگنل کس قسم کے ہو سکتے ہیں فار ایگزامپل اسکوائر انٹیگریبل فنکشن یا کوئی اور ایسا سسٹم کیونکہ کوانٹیفیکیشن چاہیے نا میری آپ کی دلی خواہش یہی ہے کہ یہی ہو مطلب پہلی کوشش پہلی خواہش پہلی آرزو یہی ہے کہ میں سسٹم کو ایک بلاک کے طور پر لوں انپٹ اپلائی کروں آؤٹ پٹ اپلائی لیکن انفارچونیٹلی اگر آپ ٹرانسفر فنکشن بناتے ہیں اس کو تو یو ہیو ٹو لوز انفارمیشن because you are now banking on it in a linear system. Transfer function linear phenomenon. Why? Because it has to relate input and output in this certain way, which is given by this particular Laplace transform. اور میں جائیں گے کچھ اور ہے Z میں جائیں گے کچھ اور ہے دونوں کا ٹرانسفر ڈومین کچھ اور ہوگا Z میں جائیں گے تو یونٹ سرکل آ جائے گا اس میں آ جائیں گے لیفٹ آ جائے گا Why? Because it has been devised that way. ہم نے کیا assumption لی ہے لیپلاس کے اندر سب سے بڑی جو بھی فنکشن ہے ٹھیک ہے تو اس کو میں نے e پاور مائنس ایس ٹی سے ملٹیپلائی کیوں کیا آئی وانٹ ٹو کیپچر دیٹ مور انفارمیشن اور آئی وانٹ ٹو میں دریا کو پوزے میں بند کرنے والی کہانی میں اس تمام انفارمیشن کو جو زیرو سے لے کر ٹی ٹو انفینیٹی تک ہے میں اس کو ایک پلاٹ کے اندر ڈالنا چاہتا ہوں اس کے لیے میں نے ایک فنکشن ڈیوائز کیا لیپلاس میں بٹ دیٹ ڈیوائزنگ آف فنکشن واز آن سرٹن بیسس اگر یہ انیشیل کنڈیشنس نہیں ہوگی فارگیٹ اباؤٹ اٹ اور یہ سسٹم ایسا ہوگا جس کے لیے مجھے ایک سرٹن طریقے سے ٹائم انویرینس چاہیے یا مجھے اسٹیٹ انویرینس چاہیے اس کو تو وہاں تک جا سکتا ہوں جب میں چاہتا ہوں کہ میں ٹی ریکیپچر کروں تو تمام چیزیں جو میں نہیں کر پاتا اس کو اور پھر یہ کہ آئی ڈونٹ وانٹ ٹو ریلائی آن اے ٹرانسفر ڈومین آئی وانٹ ٹو ڈو اٹ تو دو طریقے एक तो ट्रांसफर करने वाला, दूसरा तरीका ये था कि हम टाइम में जाएं, और तीसरा तरीका भी टाइम का है। एक तरीका टाइम का है कि मैं डायरेक्टली जाके इक्वेशन को सॉल्व करने की कोशिश करूँ, दूसरा तरीका है कि हम इसकी स्टेट वेरिएबल डिफाइन करें और एक सिस्टमेटिक तरीके से जाएं, ठीक है। दोनों में फ़र्क ज़्यादा नहीं है, मैं एक आध एग्जाम्पल दूंगा जहाँ में थोड़ा सा क्लियर होगा। ओके, मैं इसी सिस्टम को, ये जो मेरे पास इक्वेशन आई है उसमें टी भी है और सारे वेरिएबल्स हैं, और मैंने इनपुट एक नहीं रखी है, इट कुड बी मोर, ठीक है। आउटपुट यहाँ पे डिफाइन नहीं किया, लेकिन ये मेरे पास अभी ये जो एक्स डॉट में लिख रहा हूँ इट इज एक्चुअली डी एक्स और डी, ये बताएं। इस चीज़ को मैं इस तरह लिख सकता हूँ, राइट, आई कैन राइट देम इन मैट्रिक्स फॉर्म। व्हाई आई वुड लाइक टू हैव देम इन मैट्रिक्स फॉर्म, बिकॉज मैं इनको सॉल्व करना या कॉम्पैक्ट तरीके से लिखना मेरे लिए आसान है। ओके, आउटपुट इक्वेशन अगर मैं ये लिखूँ तो h विल बी सिमिलर ए फंक्शन, इट कुड बी फंक्शन ऑफ u एज वेल, और इसको अगर मैं स्ट्रैक्ट करूँ एक मॉडल के फॉर्म में तो मॉडल कुछ इस तरह बनेगा। एग्जाम्पल ये है कि इसी इक्वेशन को जो मैंने यहाँ लिखी थी इस फॉर्म में मैं लिख सकता हूँ, है ना, बाय असाइनिंग दी वेरिएबल्स इन ए सिस्टमैटिक वे। मेरा ख्याल में फिजिकल सिस्टम, इलेक्ट्रॉनिक सिस्टम्स अगर हो तो आइडिया है कि वेरिएबल्स क्या होते हैं, मैकेनिकल सिस्टम्स हो तो भी आइडिया है आप लोगों को क्या होते हैं वेरिएबल्स, और इलेक्ट्रोमैकेनिकल हो तो उसमें भी। तो अगर आगे थोड़ी देर किसी का स्लाइड पूरा जाएगी उसमें बात करेंगे वाली। ये एनीबडी इज हैविंग एनी क्वेश्चन ऑन दिस, ये आइडिया है आप लोगों को, गुड। और मैं फिर एफ इस तरह लिख सकता हूँ और मैं इसको जनरलाइज कर सकता हूँ। अगर एक सिंगल इनपुट सिंगल आउटपुट सिस्टम है इस तरह का, रफली इस तरह का, तो मैं इसका मॉडल कुछ इस तरह बना सकता हूँ, ये दोबारा लिख सकता हूँ इस तरह। मैंने क्या किया है, सी डबल डॉट को एक तरफ ले लिया और बाकी को एक तरफ ले लिया, और अब मेरी ख्वाहिश क्या है कि मैं मालूम करूँ कि इसका इंटीग्रल क्या है, फिर उसका इंटीग्रल क्या है, वो मेरी स्ट्रिक्ट वेरिएबल। मैं क्या करता हूँ कि आई जस्ट टेक डबल इंटीग्रल हियर, तो आई एंड अप हियर। डबल इंटीग्रल की वजह से ये u बन जाएगा, और यहाँ से ये जो फर्स्ट डेरिवेटिव है वो इस तरह हो जाएंगी, और इसका फर्दर आ जाएगा डबल इंटीग्रल। और मैं डिफाइन करता हूँ वन वे ऑफ डिफाइनिंग स्टेट्स, जब मैं x1 को कहता हूँ कि पूरे का पूरा x1 एंड देन x2 इज दिस, तो जब मैं इसको इस तरह डिफाइन करता हूँ और आगे लिखता हूँ तो आई कैन राइट y दिस फॉर x1 डॉट गिवन बाय दिस एक्सप्रेशन। मैंने फिर सब्स्टिट्यूट किया जहाँ जहाँ भी वैल्यूज आ रही, एंड नाउ फ्रॉम हियर आई कैन राइट दैट जो मेरा f बनेगा वो फिर किस तरह बनेगा, और जो मेरा दूसरा इसके साथ u का पार्ट आ रहा है ये बनेगा। दिस इज नॉट at this moment exactly x dot equal to x plus bu, लेकिन ये है without actually writing a b c, काम तो वही। तो ये डिफरेंट वेज हैं, डिफरेंट मीन्स हैं जिससे आप ये काम करते हैं। जरूरी नहीं है कि हम उसी पे स्टिक रहें, मतलब आप अगर डायरेक्टली सॉल्व करने जाते हैं तो वो भी तरीके हैं, विदाउट एक्चुअली टेकिंग दोज नेम्स के हम ये a b c भी लिख रहे हैं। इट इज द वे, सारी कहानी है कि वी हैव टू सॉल्व for output, and output comprises of or constitutes state. State क्या है? State is the behavior or the variable of that system doing something which needs attention, which may be manipulated, which may be redone in a certain way to get something done. मैं बड़ा example दिया करता हूँ। ये दरवाजा है, दरवाजा है, अभी यहाँ पे मौलिक है, खड़ा है। अगर मैं इसके ऊपर टॉप लगाता हूँ तो जाता है और जाके बंद हो जाएगा ना। ये टॉप कहाँ गया? टॉप कहाँ गया? टॉप
यूटिलाइज हो गया उस सिस्टम को डिजाइन,
इवेंचुअली जो पोजीशन होगी जाके रुक गया होगा। रुका इसलिए कि अगर ये होता फ्रिक्शनलेस